All right. So unfortunately, now we have to have a rather detailed discussion, I think, in the interest of ethical presentation of a topic. We need to have a detailed discussion of alphabet size. I've mentioned before that this doesn't matter, but we really need to be careful in justifying it because the alphabet size in particular affects not just the Turing machine that's solving the problem, but it also affects the set of languages that we're talking about. And so let me say what I mean by that. So what I wrote here is that if we want to talk about replacing one alphabet with another, we must also talk about correspondences between different languages. So consider, for instance, the factor problem. Remember, fact is the problem. Given an integer, does it have a non-trivial factor? So numbers that factor are 4, 6, 8, 9. Non-trivial means not one and not itself. So 1 does not have a non-trivial factor. 2 does not have a non-trivial factor. 3 does not have a non-trivial factor. 4 is the first one that does. 4, 6, 8, 9, 10, etc. Right? This would be the standard way to write down the factoring problem. Remember, a decision problem as a set is the set of all the yes instances. It's the set of all the yes answers to this. So, you know, here we have this as the factoring problem. The alphabet is implicitly this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, when we're writing down languages, when we're writing down Turing machines and stuff, we might be, thinking about solving the problem by imagining that these symbols have some meaning as numbers or something like that. But to a Turing machine and to kind of the theory of computability theory, we don't really care. We're just viewing these as strings of symbols. So if I write down, the number 8090, not 8900, this is a number, sure, but the Turing machine and the language even sees this as a string of symbols. Um, it's not really a number. And so implicitly, what factor really is, it looks like a set of numbers, and it is, but in the computability theory sense, it's really just a collection of strings over this alphabet, which has the standard digits, right? These are the digits. And this is the natural way to represent the language. But there's other ways to represent the language. For example, you know, uh, what if I want to decide this problem using a Turing machine over the alphabet 0, 1? Or really, rather, the standard Turing machine that we like to use is one that has 0, 1, then also has like a triangle and a blank symbol, right? What if I wanted to use this? I mean, that's not the same alphabet, right? So, um, what I need is a coding um, between, maybe I'll call it sigma. Well, let's ignore the triangle and the blank for now. Let's just think about the binary alphabet. Sigma b equals 0 and 1. So I need a coding between not the languages themselves, but between the alphabet, sigma d and sigma b. D stands for decimal, B stands for binary. So what's the idea? Let's think about what would be a natural idea. Um, how about this? How about I just associate 0, obviously, with 0? How about I associate 1 with a 1, obviously? What about 2? Well, now I'm out of symbols. So the easy thing to do would be to use two symbols, right? So I would say maybe 1, 0. And then I can make 3, I could associate that with 1, 1. What I'm really doing here is I'm counting in binary. 4, I would associate that with 1, 0, 0. 5, I would associate that with 1, 0, 1. 6, I would associate that with 1, 1, 0. 7, I would associate that um, with 1, 1, 1. 8, I would associate with 1, 0, 0, 0, and then 9 I would associate with 1, 0, 0, 1. So, I mean, these are just the binary representations of these numbers. Now, the idea essentially is now I can represent, say 10 as the binary digit 1, as the binary encoding of 1. So 10 really is two symbols, right? 10 is just is the symbol 1 joined with the symbol 0. So I would replace it with the symbol 1, the coding for 1 followed by the coding for 0. Then for instance, let me zoom in a bit. So then for instance, 30, let's think about the number 30. 30 would be 110, right? It would be 1, 1, that's the 3, and then 0, that's the 0. However, there's a problem. Problems. Let's just look at the number 111. It's easy to encode 30 with 110. That's an unambiguous task. But then 110 itself, well, 110 is 6, though, right? It's 110 is 6 if I look this up. Or wait, is it, what else could it be? I could think of the 1 as I could think about this 1 as the first digit and then 10. So that could also be 12. Which is it? Is it 6 or 12 or 30? It's ambiguous. The problem, if you wanna really pin down what the problem is here, it's that there are code words. We have code words, right? And some of the code words are prefixes to other code words. For example, 1 is the code word for 1, but then code is also the prefix to 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9. So it's unclear now. So basically, if I have a computer that's like reading the symbols one at a time, it sees the symbol 1 and it has no idea whether to stop and say, oh, this is the digit 1, or to keep going. Um, and so, there's sophisticated ways to get around this if you get into like information theory and such, but we don't care that much. What we're going to do to get around this, make all code words a fixed length. So in other words, instead of 0 being associated with 0, instead, don't do that. Instead, have 0 be associated with 0, 0, 0, 0. The maximum number of digits we need is 4. So I just put a 0 here, I 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 put 2 zeros here. I just pad zeros. I just pad leading zeros. So what that's going to do is that, now my machine can unambiguously decode because um, it can look at the first 4 numbers and it knows when to stop. It's looked at 4 numbers, so now it knows what is it. Was it? Now it can tell. Um, so pad with zeros. Pad with zeros. So all lengths are the same. This kills this. This gets rid of the ambiguity problem. Um, by the way, how many symbols do I need? How long should it be? So, I mean, if I have a sigma, if I have an alphabet that's like length, I don't know, 26, and I want to code that in this manner using I don't know, a new alphabet that's, I don't know, 3 symbols. How do I know how many symbols I need? How do I know how many like symbols in sigma prime is going to equate to a code word for a single symbol in here? And the answer to that is, I'm just going to write it down. I'm not going to say this in too much detail. Um, Code word length is log, I'm just going to write this down. I'll let you kind of figure it out yourself why this is true. It's log, damn it, log base the length of the smaller alphabet um, as a function of the length of the larger alphabet, and it's the ceiling of that. So I round up. So just to give you an example of why this works, we can just plug in the digits as an alphabet and the binary is as an alphabet. So this is log base 2 of 10, right? There's 10 symbols in the 0 through 9 alphabet, 2 symbols in the 0, 1 alphabet. The ceiling of that, uh, you don't need to know exactly what log base 2 of 10 is. 2 to what power makes 10? Well, 2 to the third power gives you 8. So it's log base 2 of 3 point, I don't know, something. Ceiling of that. Oh, wait, sorry. Not log base 2 of 3 point something. It's just the ceiling of 3 point something, which is just 4. So this will always work, this formula. If you're familiar with logarithms, you might want to think a little bit about why this is true. I'm not going to make a big deal of it. So let's do one more example of this. I might split this up into 2 videos. One will kind of explain what the idea is, and another one we actually write out the proof, or at least sketch the proof. So what we have now, let me write this down in text. What we have now, I'll do another example so that you can understand it better. What we essentially have is a standard method for coding the symbols of one alphabet with symbols from any other alphabet, any smaller alphabet, I should say. So let's do one more example of this. So as an example, let's let sigma 1 equal A, B, whoops, A, B, C, D, E, F. All right. And let's let sigma 2 equal alpha, beta, gamma, Greek letters. Now, the algorithm is essentially, we got to label one of these the smallest and one of these the biggest, right? Essentially up here with my binary alphabet, I was kind of thinking about 0 as the first one and 1 as the second one. And we always kind of need to do that. We need to kind of order our second smaller alphabet. So I'm going to say alpha, smallest, the gamma, largest. And so then the coding is going to be like this. Also, to kind of figure out how many symbols from sigma 2 I need to encode one of these guys, I can use my little formula log base 3, that's the length of sigma 2, as a function of the length of sigma 1, which is 6, ceiling of that. 3 to what power makes 6? Well, 3 to the second power makes 9, which is too much, so it's going to be the ceiling of 1 point something, which is 2. So I should only need 2 symbols. So let's go ahead and let A, how are we going to code that? Well, let's just encode it with alpha, alpha, alpha. Oh, wait, sorry, that's 3 symbols. Alpha, alpha. Let's let B be encoded by alpha, beta. Let's let C be encoded with alpha, gamma. We'll let D be encoded with alpha, wait, and now I'm out of symbols for the first digit, so now I'm going to increment the second one. So beta, alpha. I'll let E equal beta, beta, and then F will be beta, gamma. And so this is kind of the same kind of algorithm used to encode the symbols. So this is kind of a mechanical way to kind of relate, and now that I've done this, I can relate any language in this alphabet to a language in this alphabet. So for example, if I had the word dad that would now equate to the string in the second language. It would equate to beta, alpha, 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 beta, alpha. So the association between the alphabets, yields an association between the languages. So, factorial, for example, I already wrote down above. It's 4, 6, 8, 10, 9. I forgot 9. Dot 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 or dot dot dot. But in our binary encoding, fact is a new thing. This is the issue, is that it's sort of two different languages if we're not careful. It's this, but then it's also, 1 0 0 or 0 1 0 0 0 1 1 0 1 0 0 0. That's 8. For 8, 8 plus 2, so 1 0 1 0. That's 10. And then 1 0 0 1. That's 9. Dot dot dot. This is the factoring language in the binary alphabet. This is the factoring language in the regular alphabet. So when I define the set R to be the set of languages decidable by a Turing machine, is factoring in here twice? Are both of these languages in here? Are they set? Do I have a copy of this? Well, that seems kind of bad. I probably don't want that. So what we should do is we should fix an alphabet. So that same languages up to different encodings like this don't occur. But if we do that, how do I know that I'm not missing anything? Now, what I showed you up here, what I showed you down here with the beta and the alpha and the gamma, this is kind of a trinary or tertiary, I'm not sure. It's not a binary encoding, but it uses 3 symbols in kind of the same way that we use 2 symbols here. And the way we use 2 symbols here was sort of a binary encoding. So what I've outlined here kind of in this, what I've described as a standard method is sort of a standard method for like an encoding scheme that actually makes good use of the number of symbols here. Our encoding scheme that we're going to use for this proof is actually actually way stupider. We're going to use a much coarser, much more primitive encoding scheme. So let me describe that. Even simpler encoding using, it's going to still use the alphabet. I'm going to call it sigma b 0. It's just 0 1, just the standard binary alphabet. But we're going to use a much dumber encoding scheme. So let's encode the same set that I did in my last example. A, B, C, D, E, F. So the encoding scheme is going to be this. You're going to hate this, but it's going to make the proof easier. A is going to code to this. I'm going to kind of label them. I'm going to say A is 1, B is 2, C is 3, D is 4, E is 5, F is 6. So A, being 1, is going to be 0, 0, 0, 0, 0, 1. B is going to be 0, 0, 0, 0, 1, 1. C is going to be 0, 0, 0, 1, 1, 1. D is going to be 0, 0, 1, 1, 1, 1. E is going to be 0, 1, 1, 1, 1, 1. And then finally F is going to be 1, 1, 1, 1, 1, 1. So this is about the stupidest encoding scheme that you could think of that works properly. Whoops. It's very, very simple, and that's sort of the point. Because simple encoding schemes make for simple, if inefficient, proofs. And the inefficiency doesn't really matter a whole lot. It doesn't produce anything meaningful. Now, I want you to note actually something conspicuous, which is that we never used 0, 0, 0, 0, 0, 0. We never used nothing but zeros. And the reason for that is because we're going to reserve that for blanks in the simulation we're going to do. Let me explain. What I'm going to say though, by the way, is I'm going to give this a name. Call this the standard unary encoding. Okay, so let's write down. We're finally ready to kind of do the proof. So or to write down the statement. So here's the theorem. Let M be a Turing machine over the alphabet sigma. I'm gonna call it sigma M for the machine alphabet. Uh, then there is a Turing machine M prime over the alphabet um, uh, sigma B 01. Notice there's no blank and there's no triangle. So I could call this 01, and I haven't, I might, but, or if you'd rather, you could call it 0 and 1. You could also just call it like you could also call it blank triangle if you want. You can look at the 0 here as a blank and this is a triangle, and kind of view it as an ultra simplified Turing machine in that way, where you have nothing extra aside from the requirements. But for our purposes, we're probably just going to look at 0 and 1. Um, Over the alphabet 0, 1, which halts on all the same outputs, all of the same outputs as M, up to the standard unary coding. Um, but before I write that, it halts on all the same outputs as M, and accepts, rejects all the same inputs as M. Both of these are up to, of course, the standard unary encoding. Um, and not only that, if M operates in space slash time f of n, or I should say O of f of n. Well, I'll say f of n. F of n, then and by the way, when I say this, I'm not saying that it operates in the same f of n for space and time. I'm just saying take space or time. The statement applies to both. So if M operates in space time f of n, then M prime operates in space time O of f of n, meaning the time and space classes we're going to define, because they were defined in terms of O of f of n, are the same. Let R sub, let's say, sigma be the set of all languages over the alphabet sigma, which are decidable by a Turing machine, right? Um, then basically what this theorem is saying is that you can pick any alphabet you want. So here's R sigma. And then, maybe I'll just draw another one. And then maybe I'll draw it separate. No, I'll draw it kind of layered. I want you to kind of think of this picture as if it's 3D. So like this thing is kind of moved forwards in space. And so basically what I'm saying, and this is R again, but it's R in our like binary alphabet. And so what I've basically done is take a language here. This is a language under like the standard. This is like a language under whatever's natural to express that language. So maybe if this is a factoring problem, then this sigma here is the digits. Now I have kind of a standardized way that connects that language to this language over here, a language in the standard unary alphabet. There's a one-to-one correspondence between those two things. And then, that's true for any of these guys. There's going to be an associated one-to-one correspondence. Obviously there's no languages in one of these classes whose standard unary representation is not in the other, and vice versa. But even more than that, because the time and space classes are the same, basically what I'm saying is like it's kind of structure preserving. So if I looked at the set P, let's say, P is right here. P contains, let's say, these two languages. I know that P in the other sense, P in this language, the set of all languages over the binary one, this version of P, I'll call it like P sigma B, and I'll call this P sigma, it's going to contain the same things. So, in other words, I would never have the case where like this happens, where I end up with a language that's in P over this language, but not in P over this language. That never happens. So basically what I'm trying to say is that the structure that we're going to derive in any one of these is going to be the exact same structure in any other one. In other words, I have technically a completely different set of objects um, in our computation space, essentially, for any alphabet, but that these are all just kind of virtual copies of each other. They're all the same. Uh, R over one alphabet is the same as R over the other alphabet. P over one alphabet is the same as P over the other alphabet. NP over one alphabet is the same as NP over any other alphabet. It's always the same, no matter what. That's what I've basically shown here. And so because of that, we can kind of simultaneously do two things at once that sort of seem like opposites. One, we can fix an alphabet and say, okay, I am here. I am fixed. I'm going to be fixed on this binary alphabet. I can kind of think about all languages, no matter what I'm doing, as just kind of strings of binary symbols, zeros and ones. I can think of it that way. Alternatively, I can say I can also alternatively work with whatever language I want and still know that I'm proving things about that binary alphabet space or binary computation space. Um, so I'm just going to say like all complexity classes are the same regardless of any fixed alphabet. And I can only say that because I have this standardized way to go from any one alphabet to the other. And I can define that just by having a standardized unary representation of any one alphabet. Because if I have two alphabets, L1, if I have two languages, L1 and L2, and this language is over some sigma, and this language is over some other sigma prime, then I can kind of connect this language to its natural. Whoa, no, sorry, sigma prime. I can also represent this language. Um, well, sorry. If I don't have two languages. If I have a language over, if I have a language L over some random alphabet sigma, then that has a single unique, like concrete representation in the way that I described it via that unary encoding over my binary strings. There's only one language that represents this language in the binary encoding scheme. And then I can also go from that to any other language. So if I have some other language sigma, if I have some other alphabet sigma prime, there's only one way to go from that to this. And so because of that, I've kind of formed a link between these two. I can go from a language in any one alphabet to the corresponding language in every other alphabet by going first to my binary alphabet, um, and then thinking about how that would go connect to the new alphabet that I want to go to. So in other words, alphabets are completely interchangeable. It's a simple fact that's really complicated to try to justify, but that's the fact.